So you can figure out the horsepower of your car. It's fairly easy. Okay, so a couple of things you need to know about your car. Number one, look up its weight in terms of pounds, and then try your best check to see how long it takes to measure the time. Okay, I think we can make this a lab project for next week. Okay, so you will go from 0 to 60 and just time it. Okay, it should give you the average power of your car, the engine, and then you can compare it to the listed power. Okay, so just look it up on the internet. It's kind of neat. So the car is going to go from 0 to 60 miles per hour within this time period, so which means that the car is going to accelerate in the forward direction. Here's the mass of the car. All right, and initial speed is going to be 0. It goes from 0 to 60 within 7.4 seconds. Okay, so it's like a regular family car, so that's not bad. So what's the power of the engine in terms of watts and the horsepower? All right, so do the conversions to the metric units. All right, so the next thing we need to do is we need to figure out the right formula. So the power is going to be located here. So here's the formula for power. And obviously, it's how fast energy gets converted into kinetic energy of the car. So that's what we're going to be looking at. So write out the formula. So it's how fast the work is done, how fast the energy gets converted into kinetic energy of the car. So kinetic energy, by definition, is going to be 1/2 mv squared. So right here, so it becomes this. All right, so the speed goes from the initial speed to the final speed. We know that the initial speed is 0, so that term goes to 0. All right, so that's it. All right, so we'll do a back substitution. And then just clean it up. All right, that's the final expression. And then plug the numbers in. You get an expression in terms of watts converted to horsepower. And it says the car's horsepower is 90 horsepower. All right, it's reasonable. Okay, that's how you can figure out the horsepower of your engine. And this is something that you will do maybe next week or week after, because I got a bunch of take-home labs for it. Okay, this week's take-home lab is going to be a 3-file experiment that you will do. Okay. Okay, this is a bit of a challenge problem. All right, so notice that this car is climbing up a 10-degree hill in essence. It's doing so at a steady speed, so constant speed of 60 miles per hour. So there's a retarding force acting on, so that's the frictional force, the surface force. So the question is, what's the power required for the car to climb up this hill at a constant speed? All right, so how would you do a problem like this? All right, so I will just redraw this. I'm just going to get the center of mass. All right, so the hill is set to 10 degrees with respect to the horizontal. It's got mass, so that's just a 3,000-pound car, just like the previous one. It's got weight in the downward direction, so it's sitting on a surface. So I'm doing my force diagram. It's got the normal force going in there. It's going to be 90 degrees to the surface. Retarding force is the frictional force opposing motion. And it's moving at a steady speed in this direction, so which means that there's going to be a drive force in this direction. Thrust, the drive force, propulsive force, propulsion. Okay, I'll use D for the drive force. All right, because I get a force diagram, what I need to do is I need to express my forces on a coordinate system. So I'll have my x-axis parallel to the surface. All right, so the y-axis is going to be 90 degrees to it. All right, so that I can do my force summations accordingly. All right, so this angle is the same as that angle. All right, so this is what I'm pointing out here, this little thing that I did. Reason why you guys did so badly, and just about, with the exception of 1 or 2 of you guys, most of you guys usually struggle with mathematics. Okay, so which means that you need to spend a little bit more time practicing it. You cannot solve these problems unless your force diagram is set up correctly. So which means that you guys are either memorizing it or obviously you're looking it up. You don't have a choice, you're looking it up. And almost like, because it's almost like a take-home test, you're thinking, oh, I can just fake it, because if it were an in-class test, I would not let you use your notes. Okay, if you don't practice it, this is not something that you can come up with within the last minute. Okay, your force diagrams are not set up right to justify your solutions. If you don't set it up and you are just solving it as if it's a math problem, it shows. You guys there are 1,000 assumptions that go into solving these problems, and your assumptions are not clarified. You're just dropping equations all over the place, and you are assuming that this is an algebra problem, which it's not. So it's glaringly obvious that you have no idea what you're doing. All right. As a result, I'm forcing you to take those tests, which means that you have to do an upgrade on it, because your work does not justify. The way you set it up, it does not justify a solution. Notice that every time I'm setting something up, everything is clarified. All right. This is called showing work. When you do a test problem, you show work in a sense that it's almost like explaining what you're thinking to someone who doesn't know what you're saying. All right. That's what I do when I lecture. I just set it up. And I've been setting up from the first day on. I say, here's the format. Through this format, we will communicate. Everything in life is formatted, guys. Everything in life is formatted. You cannot communicate outside of any sort of format. All right, we speak English in the United States instead of something else. If somebody says to speak a different language to you, you won't be able to communicate. We use the Arabic numerals as opposed to the Roman numerals. We have a great alphabet that we're using. In physics, in sciences, it's the same. We use formulas that everyone agreed on. Once again, force diagrams. I mean, force diagram justifies a solution. Everything is going to come out of this. Most of you guys have half-assed force diagrams. I could have done it. I can still do it. It's not a big deal. But it's a college physics course, so I'm thinking, okay, it's not a big deal because it's more of a math literacy at this point, more than anything else. You won't be using it for the most part. Still, if it's not set up correctly, everything else that you do after this, if this is not set up right, I can just easily give you 1 point and say we're done. All right, so you have to just make sure that your force is set up correctly. When you set up forces correctly, this data literally has to go here because these are similar or identical triangles in essence. Okay, once this is set up correctly, then you could do anything you want. So everything else is going to be justified based on this. All right, so this is a good exercise. So I'm doing my conversions, obviously. Before I forget, I want to say that the forces, the speed is going to be constant because it says speed is steady speed. And the rest of it is, I'm looking for power. All right, so my power equation is going to be located here. Okay, so power, in this case, what is it that I'm looking for? Because now I have to make a decision. Okay, so I'm going to pick an equation based on what's given to me. All right, so notice that I got my speed. So the speed is given. So I say, okay, I know the speed, so it makes sense to use this equation. So power is going to be how fast this force is going to be transmitted. All right, so that's the one that we will get to use. All right, so the next question is, when you put this up, okay, notice the thing that I did. I'm going after power. I'm picking my equation, and I just explain why I end up picking this one. Because the only reason why I'm picking this one is, as opposed to anything else, is because the speed is given. And so it makes sense to use that one. Next question is, what is this force? Okay, now this is where it gets kind of complicated. And this is where you guys usually get really nailed on the test. Because you're just going to, if I give you a problem like that, I know you will follow exactly what I did, thinking that there's a secret recipe. I'll look at it and immediately I will understand what you're doing. In reality, that's not the way this works out. You have to justify it. You have to assume that the person who's grading has no idea what you're doing. All right, so which force do you use? Well, now you have to really dig into the meaning of this formula. What this means is this power comes from this force being transmitted at this speed. All right, so this is the drive force. This is the force that drives the car. So it cannot be the frictional force. It's definitely not the weight. It's not the normal force. So it's the drive force. It's what's generating the power at this point. So I go, okay, so this has to be the drive force. Okay, I would explain that if I'm solving a problem in writing, obviously. I'm just going blah, blah, blah. I'm just telling you what it is. So this force is the drive force that generates the power. Immediately I go back, I make FD, and all of a sudden I interpret the formula for our purposes. Drive force is not given to you. That is not that easy. So where do you get drive force from? I mean, there's no drive force, but there's some information here that I can utilize. I know that this car is going up at a constant speed. I can come up with a drive force because it's also the motion along the x direction, right? So I can sum up the forces along the x direction. So that's what I'm going to do. Just sum up the forces along the x direction. Drive force is in the positive x direction. Frictional force is in the negative x direction. So that's going to be negative. On top of that, here's the reason why this setup is really important. W, weight, also has a component along the x direction. It's got a component along the negative x direction. So the component of W is in this direction. It's the opposite over the hypotenuse. So this is hypotenuse, this is the opposite side. So opposite over the hypotenuse is going to be the sine of the angle of W, which is the sine of the angle of mg that we're looking at. So there's going to be a negative here. So it's going to be mg times the sine of that angle. Okay. There's no way you can come up with this equation if this is not set up correctly. All right. There's no way. In real life, it doesn't happen. So everything is connected to each other. Everything has to be just right. This is like the house of cards. If you're faking something, everything is going to come back down. Everything is just going to collapse. And most of your solutions are kind of like, it looks like physics, but it's like movie physics. The gibberish stuff that you see in the movies on the board, I look at it, I go, oh, okay, I see what's going on. All right. And so the net force along the x direction is going to be responsible for the acceleration along the x direction. So what's the acceleration along the x direction? Well, along the x direction, the speed is along the x direction. All right, I should have specified that. Now I'm talking about it. All right, so obviously its speed is along that direction, but it's a constant speed, so which means that there's no acceleration. So speed is constant. The direction of motion, which is the x direction, so there's no acceleration here. So which means that now you can isolate d. I'm just going to move all the terms to the right, and then just substitute that into that formula. And that's it. right? So that's it. So we have an expression for F. We know the mass of the vehicle. We know what G is. We know the angle. We know the speed. It's going to be 60 miles per hour. So just plug the numbers in. Do your conversion. And the horsepower in this case is going to be 110 horsepower. So that's car, the exact same car that we were dealing with. All right, so for a car to be able to go up at a steady speed of 60 miles per hour up this incline, it's going to be 110 horsepower. All right, so that was question number 14. All right, so jump in whenever you guys are ready, if you have the answer. All right, so let's come up with an example of a scenario where the final mechanical energy is larger. Okay, guys, final mechanical energy is going to be larger when there's a propulsive force at work, right? So when there's a propulsive force at work, what happens? It feeds energy into the system. Case in point. All right, so using the Geller's incline experiment as an example, what happens? This ends up gaining mechanical energy. All right, so which means that the final mechanical energy is going to be larger than the initial mechanical energy. So the energy is gained. All right, so this happens when there's a propulsive force. All right, so when there's a propulsive force at work. So final mechanical energy is going to be larger when there's a propulsive force at work. So you end up gaining mechanical energy. Okay, let's skip 28, move on to 29. Okay, so if the final mechanical energy is larger, explain where the extra energy comes from. All right, so the extra energy, yeah, go ahead.
It can come from chemical.
Very good. It could be chemical. If you're driving Tesla, it could be electrical, right? All right, what else? It could be heat. What else can you guys think of? Obviously, nuclear, fusion or fission, regardless. And then you can, I mean, just imagine, guys, the nuclear can turn into heat, that can turn into electrical. And chemical, what else can we think of?
We also said light.
Oh, we also said light. Very good. Light. What else? How about the wind? I mean, okay, heat, light. Okay, that's it. Okay, so these are the ones that I can think of right now. Okay, so these will get converted into the mechanical energy through the propulsive force, right? Okay, so give an example of a scenario where the final mechanical energy is smaller. Okay, once again, Geller's incline experiment. All right, so this time the frictional force of friction. So initial mechanical, we got the final mechanical. We got the initial final. All right, so you end up losing mechanical energy when there's friction present. Okay, so final mechanical energy, this one is going to be smaller. All right, I just messed it up. Damn, just take this down a little bit. All right, so the final mechanical energy is going to be smaller than the initial one. The initial one is here. So this is the amount of energy that we end up losing, right? So next question is, if the final mechanical energy is smaller, account for the missing energy. So what else can you guys think of? So it's going to turn into sound. Okay, if there's too much friction, surfaces will heat up. Surfaces may start to glow, so it could be light in the form of fire. If there's too much friction, obviously it can cause deformation. And what else can you think of? Okay, so those are the only ones that I can think of right now. All right, so mechanical energy is going to be smaller. This is going to be smaller than this one when there's friction present. And so the energy gets converted from mechanical energy to sound, heat, light, or it can cause deformation. That's it. All right, so what's the conservation of total energy? All right, so total energy is constant. That's what it means. So the energy cannot be created or destroyed. The total energy of the universe remains constant. So it can only be converted from one form to another. So this means that the total energy will be constant. Energy cannot be created or destroyed. It can only be converted. All right, so the race cars are designed to break apart easily because in order to take the energy from the driver, right? That's the fastest way you can take the energy from the energy away from the driver. We're talking about the energy which is generated during car collisions. Tremendous amount of energy needs to be taken away from the driver. So the easiest way to do it is just break the car apart. Lastly, the power. So power is how fast the work is done, how fast the energy is transferred, or speed which the force is transferred.